Hello, everybody, and welcome to Why Slice. I'm Lars Kotov. I'm an assistant professor of computer science at the University of Wyoming, and I'm here to tell you a little bit about my perspective when it comes to computer science, because that's what we're going to learn about. So, we should probably figure out first what computer science actually is. So, then, what is computer science to me? Well, computer science, despite the name, isn't really about computers, and it's not really about science either. In the words of a famous computer scientist, computer science is about as much about computers as astronomy is about telescopes. And that's actually a very nice analogy because in astronomy, telescopes are used as tools to investigate things. And in a similar fashion, in computer science, we use computers in many cases as tools to investigate particular things. And there is certainly a scientific aspect to that, but that is not really front and center of all of computer science. So not really about computers, and sorry, not really science either. Although there are certainly computers involved in it, and there are scientific aspects to a lot of computer science. So then, if it's not about computers and science, what is computer science actually? And to me, computer science is really something that's inherently interdisciplinary, that involves things from many, many other disciplines. For example, my background is in artificial intelligence, and a lot of the concepts, a lot of the methods, a lot of the things we do there come from statistics or are inspired by nature. So there's a biological aspect to all of these things. And of course, in the end, what we're aiming for is to produce intelligent systems inspired by humans. That requires us to know how do humans think, how does cognition work, how we can we encode this in a way to teach a computer to do the same things that we do as humans, or maybe not entirely the same things, but something similar that allows us to create intelligent tools, inject some intelligence into a computer that we can then use for specific purposes. So, what might a typical day for a computer scientist look like? Well, it really depends on what in particular you're working on. If you're a theoretical computer scientist, then your typical day might be almost indistinguishable from a mathematician. As in, you might be sitting down on your desk and you're pulling out a piece of paper and a pen and you start writing, for example, to prove something or to derive a mathematical concept applied to computer science. Your work might not involve a computer at all at this point until maybe you get to the point where you start to write up your work because you want to publish a paper on this or you want to communicate what you have found to your colleagues. But really, you would be using a computer as a tool for communication and publication purposes. In fact, not dissimilar to what you're doing at the moment because you're using your device, your computer, whether that's a laptop or a phone or a desktop computer, to watch this video. And thus, we have some way of communicating, even though that is very much one way, as in, I am speaking to you, and I don't even know that you're watching this at the moment. But all of this is really enabled by computer science. If I'm a computer scientist that's more on the practical side, then my day to day work might involve a lot of computers. For example, like I said, my background is in artificial intelligence, and a lot of that involves running large scale computational experiments. So I don't just use the laptop that is sitting right here and recording this video right now, but I also use our research computing facilities here at UW. We have a research computing center on campus, and similar research computing centers are scattered throughout the United States and throughout the world. Their only purpose is to provide computational power because I have some task, some problem that I want to solve, and that is really, really difficult. It takes a really, really long time, so I need a lot of compute power. I can go to our research computing center and create a description of the job I want it to do. This is the computational task. These are the things that you're going to need. This is the kind of thing that you would produce as output that I want you to save because I want to come back to it later and have a look at it. Off you go. And some of these research computing centers are fairly large. Here at the University of Wyoming, we have a couple of thousand cores. So you can think of this in terms of power as being very roughly equivalent to a couple of thousand laptops. And as I said, the only purpose of this is to run compute intensive tasks. which arise not only in computer science. In fact, the most heavy users of our research computing here on campus are actually in other disciplines. And this comes back to my earlier point about computer science being an inherently interdisciplinary and multidisciplinary issue and thing, because computing can help people in so many other domains. For example, in statistics, I've already mentioned statistics in relation to machine learning and artificial intelligence, but computer science can also help with statistics research itself because some of the evaluations are computationally expensive, and we might want to find a way to speed these up or run these more efficiently on given computational infrastructure. Similarly, in many areas of engineering, for example, mechanical engineering, we might want to simulate how something behaves before we build a physical thing and then evaluate that, because that will require resources and that might require special machinery that we might not have access to. If we can simulate it, that's much cheaper. We can do a lot more of this. We can run many things in parallel at the same time on, for example, our research computing infrastructure here at UW, and we can get results from that. We don't have to go and do the physical thing. So, again, computer science playing into all of that, and similarly in many other disciplines. Let's talk about something that most people probably have in mind when they think about computer science: building software. That is also a big part of what we do as computer scientists. And there are people that specialize in software engineering, which is not really the same as programming. It's more thinking about how do we architect software. And the difference here is similar to when you would build a house, for example, you need a carpenter and you need a plumber and you need all kinds of different people that take care of different parts of the house that you want to build. But then you also want to have an architect which who keeps an eye on the overall thing and makes sure that what you get out in the end is really a house and that it's suitable for the purpose that you build it for, to live in it, I assume, or to rent it out maybe, rather than ending up with a collection of different components that, while each individually work fine, your plumbing works fine, and you have great walls and you have great cabinets, but for example, you don't have any doors, that would be bad, right? Similar in software, people think about how do I build software? How do I build software in a way such that the end result is usable by the intended target audience? And that might be the computer scientists. That might be the general public. As for a lot of software, you are using software right now. I'm using software right now. We're all using software every day, whether we realize it or not. So, computer science, really a very large field that encompasses elements from many, many different fields, and not just something that pulls together things from other fields, but also something that enables a lot of the things that are going on in other fields. And then, of course, a lot of everyday activities, for example, communications. I'm sure you have used Zoom more often by now than you really want to. All of that is enabled by computer science.